Welcome to solverfy.
Question 61 is a weak base, strong acid titration with two separate problems. The first one is the weak base pyridine being titrated with the strong acid nitric acid, and it is just monofunctional, meaning it only accepts one hydrogen ion. However, the second one, without them telling you, they pulled a fast one, is difunctional, meaning it has two Kb values, it can accept two hydrogen ions, and has two equivalence points. So we need to calculate both equivalence points for the second one and the pH at each of them. Let's first start with pyridine. The equivalence point volume can be calculated by taking the volume of pyridine, 2.65 liters, multiplying it by its concentration, 0.0750 molar, to get moles of pyridine. The reaction with nitric acid is 1:1. We now have moles nitric acid. To get volume of the nitric acid solution, we'll divide by the molarity of 0.447, but it wants it in milliliters, so we'll multiply by 1,000. 444.6 milliliters of 0.447 molar nitric acid are required to neutralize 2.65 liters of 0.075 molar pyridine. Now that we know the equivalence point volume, we can solve for the pH. The pyridine, when it reaches the equivalence point, will have all converted into its conjugate acid. So what we have at the equivalence point is a weak acid. We carry out a weak acid Ka calculation. To solve for pH, we need to know the hydronium concentration. We can get the hydronium concentration for a solution containing a weak acid by taking the square root of the Ka value multiplied by the concentration of the weak acid. To get the Ka value, we will look up the Kb for pyridine, 1.7 times 10 to the negative 9, and divide it into Kw. This is Ka. To get the concentration of the weak acid, the weak conjugate acid to pyridine, we'll calculate the moles of pyridine we started with by multiplying the volume, 2.65 liters, by the concentration, 0.0750 molar. This will give us the moles of pyridine we started with, which is also now equal to the moles of the conjugate acid of pyridine that we have at the equivalence point. We divide those moles by the concentration that we have at the equivalence point, by the volume that we have at the equivalence point, which is the 2.65 liters we started with, plus the 0.4446 liters that we added. This will then give us the concentration of the weak acid. So the hydronium concentration is the square root of Ka multiplied by the concentration of the weak acid. We take the negative log of that hydronium concentration and we get a pH of 3.21. Now for the second one, ethylene diamine, which is actually difunctional and can accept two hydrogens. To calculate the first equivalence point, we'll take the volume that we have of the ethylene diamine, 0.188 liters, multiply it by the molarity, 0.250 molar, to get moles ethylene diamine. To reach the first equivalence point, 1 mole of ethylene diamine requires 1 mole of nitric acid. Once we have moles nitric acid, we can calculate volume nitric acid by dividing by the molarity of nitric acid, 0.447 molar, as we did up here. This will give us liters. We will then multiply by 1,000 to get milliliters, 105.1 milliliters. Now to solve for the pH, we need to recognize that when that first hydrogen comes off, we have an amphoteric species. It's not a weak base, it's not a weak acid, it can behave as both. Because it can behave as both, we calculate pH a different way. pH will correspond to 1/2 pKa1 plus pKa2. We can look up the the Kb values for ethylene diamine and divide the Kb values into Kw, 1.0 times 10 to the negative 14, to get the Ka values. Once we have the Ka values, we can take the negative log of those Ka values, sum them up, and divide by 2. So this is Kb1 divided into Kw to get Ka2. This is Kb2 divided into Kw to get Ka1. We sum Ka1, or we take the negative log of Ka1 to get pKa1, the negative log of Ka2 to get pKa2, sum them together, divide by 2, and we get a pH of 8.39. Now for the second equivalence point. The second equivalence point will simply correspond to double the first equivalence point volume. That's because the volume required to have one hydrogen come off will be equal to the volume required to have the second hydrogen come off. So the equivalence point volume, second equivalence point volume, is another 105.1, or a total 210.2 milliliters. To solve for the pH at the equivalence point, we'll recognize that the ethylene diamine has become fully protonated and we have a weak acid in solution. To calculate the hydronium concentration of a weak acid, we take the square root of the Ka value multiplied by the concentration of that weak acid. To get Ka1, we will take Kb2 and divide it into Kw. This is Ka1. Then, to get the concentration of the weak acid that we've created at the second equivalence point, we'll calculate the moles of ethylene diamine we started with, recognize this is now the moles of fully protonated ethylene diamine we have at the second equivalence point. We divide that by the new volume. We started with 0.188 liters. We added another 0.2102 liters. This then is the concentration of the weak acid at the equivalence point. So the square root of Ka1 multiplied by its concentration will be the hydronium concentration. We take the negative log of that to get pH, and we get 3.89.